This is joint work with Anindya De, Juan Lee, and Rocco Cervedio, and like the title suggests, it's about truncated statistics. So truncated statistics is a really well-studied field dating back to work by Bernoulli in the late 1700s, and essentially shows up whenever a dataset has undergone some kind of censorship. So as a concrete example, the red curve here is just the PDF of a standard Gaussian distribution in one dimensions. And the green curve is obtained by conditioning the Gaussian to lie on points which are less than 0.5. And so you get the green curve by renormalizing the PDF so that it integrates to 1. And this field is extremely active even today. There's entire book-length monographs being written about the subject. And within TCES, there's been a lot of work on learning and parameter estimation when given samples from a truncated distribution. So a recent line of work considers the problem of learning parameters of the original distribution or learning the original distribution when given samples from a truncated distribution, a truncation of the original distribution, subject to some conditions. So as an example, on the left over here is a draw of 1,000 samples from the two-dimensional standard Gaussian distribution. And on the right is a draw of 1,000 samples from a truncated two-dimensional standard Gaussian distribution. And the truncation is maybe kind of clear. It's given by this purple slab. And if you call this purple slab K, then this is just the notation I'll be using for truncated distribution. So just N0, 1, 2, vertical line sub K, right? And so a very basic question is if you can distinguish between these two cases, or in other words, if you can detect truncation. So the broad question which kind of motivates this work is the following. Given sample access to either some distribution D or a truncation of this distribution D, how many samples do you need to distinguish between these two cases? And again, D sub K is just the notation I'll use for the truncated distribution. But this question is somewhat ill-posed. There's an immediate issue, which is that if the set K has measured really close to 1 under the distribution D, or in other words, if you delete or censor a very tiny part of the distribution, then you won't be able to detect censorship or truncation at all, right? Or in other words, if the total variation distance between these two distributions is very, very tiny, then you can't hope to actually detect truncation efficiently. And so let's incorporate this condition. And so we get this new question where you're promised that you either have access to D or you have access to D condition in a set K such that the variation distance between this truncated distribution and the original distribution is at least epsilon. And we'll think of epsilon as a constant. We're not going to be too focused on dependence on epsilon. And so in a recent work with Anindya and Rocco, we showed that if you're promised that the distribution D is the standard Gaussian distribution in n dimensions, and if the censorship set is promised to be convex, then linear in n, linear in the dimension number of samples, are enough to detect truncation, to distinguish between these two cases. We also show that this many samples are needed. And furthermore, the upper bound, the number of the samples, this linear in n number of samples are not only enough information theoretically, but also the algorithm we give is computationally efficient. And so it's natural to ask if you could handle broader classes of distributions or censoring sets. The distribution here is it's a very nice distribution. The Gaussian is great, but you could hope to handle broader classes of distributions. And the class of censorship sets we handle are very structured. Convex sets are very structured. And so you might hope to relax these two assumptions. And that's precisely what we try to do in this work. So in this work, we consider the problem of detecting truncations of hypercontractive product distributions. I'm not going to formally define what these distributions are, but I just want to say that hypercontractivity is a very standard, very natural property. It's used especially in Boolean function analysis and related areas. But as concrete examples of hypercontractive distributions, it turns out that the standard Gaussian distribution, the uniform distribution on the solid cube, as well as any finite product distribution. So in particular, the uniform distribution on the Boolean hypercube or on any finite set, all of these distributions are hypercontractive. So we handle a much broader class of distributions than the previous work by DNS in 23. And we don't just handle convex truncations. We don't handle convex truncations. We handle truncations by low-degree polynomial threshold functions. So this is, again, a very well-studied class of functions in theoretical computer science. People have thought about learning, testing, de-randomization problems for low-degree polynomial threshold functions. Let me just remind you what these functions are. So a polynomial threshold function is defined by a polynomial. So degree D polynomial threshold function is defined by a degree D polynomial on Rn. And it's just the indicator of this polynomial being bigger than 0. So when d equals 1, the polynomial defines a hyperplane. And so the polynomial threshold function is a half space defined by this hyperplane. And d equals 2, a concrete example is an ellipsoid. But, polynomial threshold functions don't have to be convex. So in some sense, they are not as structured as convex sets. So in this work, we consider the problem of detecting truncations of hypercontractive distributions, product distributions, by low-degree polynomial threshold functions. And as a running example, you might just want to keep the uniform distribution on plus minus 1 to the n, the Boolean hypercube, in mind for the rest of the talk. So our main result is the following. Given, say you want to distinguish between access to D versus D conditioned on a degree D polynomial threshold function, we require one minor technical condition, which is that the measure of the polynomial threshold function is not too small, the measure under D. But I'm going to sweep this under the rug for now. But our answer to this question is that n to the d over 2 samples are both sufficient and necessary to solve this question. And our algorithm is, again, computationally efficient. So let me say one quick sentence about this upper bound, but the upper bound before I give you a sketch. So a VC dimension or a learning type argument allows you to show that n to the d samples are enough to detect truncation. And so our main contribution from the algorithmic side is that is kind of a more efficient way of detecting truncation rather than learning. And the learning-based algorithm is not necessarily efficient in terms of runtime either. So let me tell you a little bit about the upper bound in a very concrete setting. So let's say the distribution you're interested in detecting truncations of is the uniform distribution on the Boolean hypercube plus minus 1 to the n. And so the main idea behind the algorithm is pretty simple, but it requires a little bit of notation. So given a point x in the Boolean hypercube, you can define its polynomial kernel obtained by kind of looking at these monomials of size at most d. Yeah, so this x tilde is a vector indexed by subsets of n of size at least 1 in at most d, and x sub s is just the product of xi's, where I is in the set S. And in the main idea behind the algorithm is essentially the following. In the untruncated setting, or in other words, under the uniform distribution on the Boolean hypercube, on average, the length of this kernelized vector, this x tilde vector, is going to be 0. It's going to be really close to the origin, in other words. But in the truncated setting, using hypercontractivity of the uniform distribution on the Boolean hypercube, you can show that it's a constant away from 0, a constant which depends on the degree d of the polynomial threshold function that's causing the truncation. And so this suggests a very natural statistic. It is a little, in the interest of time and to keep things simple, I'm not going to write down the statistic. And so we can compute the statistic, which distinguishes between these two settings, but we also require that the variance of this estimator or statistic is the same in the truncated and untruncated settings. And over here, again, we kind of need hypercontractivity to control the variance. And when you try generalizing beyond the Boolean hypercube to arbitrary hypercontractive distributions, you run into a kind of an annoying technical issue, which is called this linearization problem. And it's essentially, it shows up because over the Boolean cube, if you take the Fourier basis given by the parity functions, the product of two parity functions is another parity function. But if you look at the Fourier basis of a hypercontractive distribution, the product of two basis elements isn't necessarily a basis element. So you have to expand it out in terms of the basis and do a little bit of work to kind of make this idea go through for arbitrary distributions. Right? And so with this out of the way, I'm going to turn to the lower bound. The lower bound is, we proved this again for the setting in the setting of the Boolean hypercube. So in particular, we show that the following distributions are identical. Let's say you draw little o of n to the d over 2 samples from, in one case, the uniform distribution on the Boolean hypercube. And in the other case, from a truncation of the uniform distribution by a degree d polynomial threshold function. I'll tell you what this distribution over threshold functions is, but we show that these two distributions are little o1 close in total variation distance, which immediately implies that you need at least n to the d over 2 samples to distinguish between these two cases. And so let me tell you what the distribution over PTFs we use is. So a draw from the distribution is going to be as follows. We look at degree d homogeneous polynomials, so all monomials of size d, but their coefficients are going to be independent standard Gaussians. So g of s is going to be a standard Gaussian random variable. And the polynomial threshold function is obtained by just taking the indicator of this polynomial being bigger than 0. So these polynomials are well studied in the literature. They're called Gaussian random polynomials. And we kind of rely on essentially a pseudo-randomness type of property of these polynomials. And we also rely on a very recently proved bound on the variation distance between Gaussian distributions due to Devroy et al. In 2022, I believe. Right. So to summarize, our main theorem is both a tight upper, is an upper and lower bound, matching upper and lower bound for the problem of detecting truncations of hypercontractive product distributions by low degree polynomial threshold functions. And to conclude, it's natural to ask if you could say similar things, if you could detect distribution truncations in other settings. And it would especially be interesting to try to do something in a non-product setting. Thanks for watching.